Space is not silent. Across the vast dark, cryptic messages are being sent, and we are only just beginning to hear them. These are not random noises. They are deliberate, powerful, and profoundly strange signals, and a growing number point directly to the most mysterious objects in existence, black holes. Today, we are decoding 25 of these unexplained cosmic transmissions. By the end, you will possess a new understanding of the universe's hidden language, a catalogue of its deepest puzzles. We will hear a rhythmic heartbeat from a feeding black hole and trace a single ghostly particle back to a monster's jet. What does it mean when a black hole suddenly goes quiet, or when it leaves a cold fingerprint on the birth of everything? The cosmos is speaking. Are you ready to listen? Our first signal was so extraordinary it earned its own exclamation point. In the summer of 1977, a radio telescope in Ohio, known as Big Ear, recorded something that would become the most famous single event in the search for cosmic intelligence. For 72 seconds, a powerful, focused burst of radio waves swept across the receiver. It came from the direction of the constellation Sagittarius. The signal was so strong and so perfectly matched what scientists predicted an artificial transmission would look like that a volunteer astronomer, Jerry Amon, circled the data printout and wrote one word in the margin: "Wow." The wow signal, it was never heard again despite decades of searching. For years, the leading theory was that it represented a deliberate broadcast from an advanced civilization. But there is another, more unsettling possibility. The frequency of the wow signal, around 1420 MHz, falls within a quiet band of the radio spectrum, a band naturally protected by hydrogen. It is a logical channel to listen on or to broadcast on, but it is also a frequency that could be generated by a natural yet immensely powerful process. What if the signal was not a message but an echo? Some astrophysicists have proposed a source that is both natural and unimaginably violent: a black hole. The theory suggests the signal could have been produced by a comet or asteroid being torn apart by a black hole's tidal forces. As the material was shredded and heated to incredible temperatures, it might have emitted a brief, intense blast of radio energy. Or perhaps it was a burst from the swirling, superheated material in the accretion disk itself, a single, brilliant flash beamed by chance directly at Earth. The duration, 72 seconds, matches the telescope's fixed field of view, meaning the signal turned on and then off as Earth's rotation moved the telescope away. This fits a point source in space. The mystery deepens because we have never found a black hole exactly in that spot, but our maps of the silent, dark objects in that region are far from complete. So the wow signal remains suspended between two profound ideas. Was it a hello from the stars, or was it the death cry of a world, amplified by the darkest gravity well in the cosmos? We may never know for sure, but its singular brilliance continues to point our curiosity toward the void. The wow signal refuses to fade into history. In the decades since that single, tantalizing blip, astronomers have subjected it to relentless scrutiny, armed with far more powerful telescopes and sophisticated computer models. One prominent attempt to demystify it pointed to a much closer and seemingly mundane source. In 2017, an astronomer proposed that the signal could have been caused by a passing comet, or more precisely, the cloud of hydrogen gas surrounding a comet. The idea was that as this comet, unknown at the time, moved through space, its hydrogen envelope could have generated the brief radio burst. For a moment, it seemed the mystery was solved. But the astronomy community quickly dismantled the theory. The comets suggested were not in the right part of the sky at the right time, and the physics of a comet producing such a powerful, narrowband signal simply did not add up. The comet hypothesis, while creative, faded away. This failure actually strengthens the case for something more extraordinary. If it was not a local object and not a repeating natural phenomenon we understand, then the source must be both distant and profoundly energetic. This is where the black hole hypothesis gains its stubborn persistence. Modern reanalysis focuses on the signal's purity and power. It was not a spread-out smear of noise, it was a sharp, clean spike on one specific frequency. Generating that requires a coherent process, something like the natural maser action found in the chaotic environment around a black hole. Imagine the intense magnetic fields and swirling plasma of an accretion disk. Under just the right conditions, this chaos can act like a cosmic laser, amplifying radio waves into a tight, powerful beam. If that beam happened to flicker across our solar system for just 72 seconds, it would look exactly like the wow signal. The skepticism is understandable. We have no confirmed black hole in that exact location. But our view of the galaxy is imperfect. We are mapping these dark objects only slowly. A quiet stellar mass black hole, not actively feeding enough to be a bright X-ray source, could easily lurk unseen along that line of sight. It might only announce itself with a rare, furious burst as it consumes a stray bit of matter. So the signal remains a ghost, a one-time event that perfectly straddles the line between a natural catastrophe and an artificial beacon. Its enduring power lies in that ambiguity, forcing us to confront the limits of our knowledge. We are left with a chilling thought. Sometimes the universe speaks only once. The silence after the wow signal was a lesson in cosmic patience. For decades, astronomers scanned the skies, hoping for another such clear, deliberate ping. What they began to catch instead were not deliberate messages but cosmic screams. These are the fast radio bursts, or FRB, millisecond-long flashes of radio energy so powerful they outshine entire galaxies. They arrive from across the universe carrying the energy of 500 million suns, packed into a blip shorter than a camera flash. Most are one-off events, a single catastrophic boom and then nothing. But one changed everything. It is catalogued as FRB 121102, the first repeater ever discovered. This was not a solitary scream, it was a voice that kept calling back. Its discovery shattered the idea that all FRBs were caused by one-time cataclysms, like a star exploding or two neutron stars colliding. Something here was alive, persistent, and capable of firing off these monstrous bursts again and again. The hunt to locate its home galaxy was a triumph of precision astronomy. When scientists finally pinpointed it, they found something surprising. The bursts were coming from a tiny, faint dwarf galaxy over 3 billion light-years away. This was not a grand spiral like our Milky Way. It was a small, unassuming cosmic backwater, yet it housed this phenomenal engine. At the very center of this little galaxy, astronomers found a persistent, faint radio glow. This is the signature of an active galactic nucleus, a supermassive black hole that is steadily feeding on surrounding gas. The evidence pointed directly to a chaotic, energetic environment, the perfect crucible for generating such violent, repeating bursts. The debate ignited immediately. Is the source a magnetar, an ultramagnetic neutron star having fits of starquakes on its unbelievably dense surface? Or is it the black hole itself? The leading theory suggests it could be a young, rapidly spinning magnetar, perhaps born from the collapse of a massive star in that turbulent central region. Its intense magnetic field could twist and snap, releasing these colossal radio shockwaves, but the black hole hypothesis is compelling. An active black hole's environment is a maelstrom of charged particles and magnetic fields. Flares from its accretion disk or interactions with a nearby orbiting object could theoretically produce these focused bursts. Some models even suggest the bursts could be coming from a pulsar, a different type of neutron star, venturing too close to the black hole and having its material stripped away in violent, periodic episodes. FRB 121102 taught us that the universe has more than one way to shout. It proved these signals could be recurring, turning a mystery into a potential tool. By studying its repeating pattern, we can probe the invisible material between galaxies and test the laws of physics under extreme conditions. This repeater is a lighthouse in the dark, and its persistent flashes are illuminating the violent nursery of a dwarf galaxy where a hidden monster may be pulling the strings. Before the repeater taught us patience, there was the original scream. It arrived in 2001, buried in old data from the Parkes radio telescope in Australia. An astronomer named Duncan Lorimer and his student were sifting through archival observations of the Magellanic Clouds when they found it. A single 5-millisecond spike of radio energy so powerful it saturated the telescope's receiver. This was the Lorimer burst, the very first fast radio burst ever identified, though it would take years for its true significance to be understood. Its energy was staggering, equivalent to the total output of our sun over an entire month, released in less time than it takes to blink. And then it was gone. Unlike the repeater that would follow, this was a one-off event, a solitary detonation in the cosmic dark. Its one-time nature pointed directly to a different kind of violence, a final, irreversible cataclysm. What natural event could be so brutally efficient, converting so much mass into a pure flash of radio waves? Theorists immediately looked to the most extreme gravitational environments in the universe. One compelling possibility is the collapse of a supermassive star, a behemoth dozens of times heavier than our Sun. At the end of its life, such a star does not just explode, its core can collapse directly into a black hole without a supernova. This sudden birth of a singularity, the instant formation of a new black hole from a dying star's heart, could unleash a shock wave through the star's magnetic field, producing that singular titanic radio burst. Another, even more dramatic hypothesis involves a pre-existing black hole and a companion. Imagine a binary system where a neutron star, itself the incredibly dense corpse of a star, orbits a black hole. Over eons, their dance decays, and the black hole's gravity finally reaches out to claim its partner. In the final moments, the neutron star is torn apart, not by tides like a comet, but by the immense forces of the black hole itself. As it is shredded and consumed, its magnetic field snaps, and the incredible energy of its destruction is channeled into a focused beam, a final radio scream announcing its demise. The Lorimer burst opened the door to these terrifying possibilities. It proved that the universe could produce these incomprehensibly brief, powerful signals. It shifted the search from looking for deliberate patterns to listening for cosmic explosions, for the sounds of ultimate endings. This single data point, hidden in old tapes, became the foundation for an entire new field of astronomy, one built on listening for the echoes of stars being swallowed whole. Deep within the silent heart of our own Milky Way, something is stirring. For years, astronomers have trained their most sensitive radio telescopes on Sagittarius, a star, the supermassive black hole that anchors our galaxy. It is typically a quiet giant, a slumbering behemoth, but occasionally it wakes up. The signals are not the millisecond screams of distant FRBs, but something closer, stranger, and deeply personal. They are intense, sporadic bursts of radio waves erupting from the galactic center and lasting for minutes or even hours. Imagine sitting by a quiet pond and watching a sleeping leviathan beneath the surface. Every so often it exhales, sending a powerful ripple across the water. These radio bursts are those ripples emanating from a monster 4 million times the mass of our Sun. So what is causing them? The leading theory is a messy dinner. Our black hole is not in a complete vacuum. It is surrounded by a swirling cloud of gas and dust, and occasionally a clump of this material, perhaps a small cloud or a fragmented asteroid, stumbles too close. As it is pulled into the accretion disk, it is heated to millions of degrees, creating a bright flash of radio emission as it vanishes. It is the black hole's digestive process, a brief flare of activity as it consumes a cosmic snack. Another possibility points to the black hole's own magnetic personality. The chaotic plasma of the accretion disk is threaded with incredibly powerful magnetic fields. These fields can become twisted and tangled, storing enormous energy until they suddenly snap and reconnect, much like a solar flare on our sun but on a titanic scale. This magnetic explosion would blast energy outward, producing the radio bursts we detect. But there is a more exotic idea on the table. Some scientists speculate these bursts could be the signatures of actual objects surviving for a time in the black hole's violent neighborhood. Could they be flares from a population of magnetars, those ultramagnetic neutron stars orbiting perilously close to the event horizon? Or perhaps even signals from strange, hypothetical objects like asteroid-sized primordial black holes interacting with the disk? Each burst is a unique event, a puzzle piece. By analyzing their structure, their polarization, and how they change over time, astronomers are essentially taking the black hole's pulse. These are not random noises, they are vital signs from the gravitational heart of our home galaxy. Every flicker tells a story about the environment just outside the point of no return, a place where space and time are stretched to their limits. Listening to these bursts is like eavesdropping on the private life of a cosmic giant, and it is reminding us that even the quietest monsters can have restless nights. Sometimes the most dangerous signals come from the smallest systems. Far from the supermassive giants, a different kind of predator hunts within our own galaxy. This is the Black Widow pulsar, a millisecond pulsar named for its lethal relationship with a nearby star. A pulsar is a rapidly spinning neutron star, the dense core left after a supernova, and this one rotates hundreds of times every second, sweeping the universe with a lighthouse beam of radiation. Its companion is a small, dim star locked in a tight, deadly orbit. The pulsar's intense radiation and powerful particle wind are slowly but relentlessly cooking and evaporating the smaller star, stripping its material away. It is a cosmic spider consuming its mate. For years, astronomers monitored this system, expecting a predictable rhythm. The pulsar's tick should be as regular as a perfect clock, only slightly altered by the orbital dance with its companion. But the signals told a stranger story. The timing of the pulses began to show strange, unexplained distortions. They would arrive slightly early or slightly late in ways that could not be accounted for by the simple two-body dance. It was as if the fabric of space-time around the system itself was subtly shifting, warping the path of the radio signals on their way to us. This is where the shadow of a third object emerges. Could there be a hidden participant in this destructive ballet? Some astrophysicists have proposed a startling idea that the anomalies are caused by the gravitational influence of a small, dark companion, perhaps a black hole orbiting the pulsar and its victim star. In this scenario, the system would be a rare triple, with the pulsar and the star orbiting each other, while both are tugged by the invisible gravity of a black hole further out. The black hole's mass would warp the space around the entire system, causing the pulsar's clock-like signals to stutter and shift as they travel through the curved geometry on their way to Earth. The evidence is not yet conclusive, but the puzzle is profound. We are witnessing a star being destroyed by a pulsar, while the very signals announcing that destruction are being scrambled by something we cannot see. It forces a question: are we looking at a binary system with messy physics, or a triple system hosting one of the universe's darkest secrets? The Black Widow may have a hidden partner, making this cosmic predation even more sinister. The clockwork precision of a pulsar is one thing, but a heartbeat from a feeding black hole is something else entirely. In the constellation Aquila, roughly 35,000 light-years away, a stellar mass black hole named Jubris 1915+105 is performing a strange, hypnotic dance. It is locked in a binary system, relentlessly pulling gas from a companion star into a swirling, superheated accretion disk. And from that maelstrom of doomed matter, astronomers have detected a signal so regular it feels almost alive, a rhythmic heartbeat pulsing in X-rays. These are not random flickers, they are quasi-periodic oscillations, or QPOS, a term scientists use for a signal that repeats at a nearly constant frequency, but with subtle variations in its timing and strength. In this system, the heartbeat is remarkably steady, repeating about every 50 seconds for years on end. Imagine standing before a colossal drum, one made of incandescent plasma and gravity so strong it bends light, and hearing it beat with the persistence of a metronome. This is not the tick of a dead star's rotation, it is the dynamic pulse of a black hole's feast. So what is causing this cosmic rhythm? The leading theory takes us to the very edge of the event horizon, to a place where physics becomes extreme. As material spirals in at nearly the speed of light, it does not flow smoothly. The inner part of the accretion disk may be unstable, periodically puffing up with hot gas before collapsing back down under the black hole's immense gravity. Each cycle of inflation and collapse would release a burst of X-rays, creating the steady beat we observe. It is like watching a fountain of fire that rises and falls in perfect, terrifying time. Another idea involves the black hole's spin. If Joris 1915 is rotating rapidly, it drags the very fabric of space-time around with it, an effect called frame dragging. This twisted space could force the inner disk to wobble or precess, like a spinning top slowing down, with each wobble directing a brighter flash of X-rays toward us once per cycle. The heartbeat, therefore, could be the literal pulse of space-time itself, modulated by the black hole's rotation. But the mystery deepens because this signal is not perfectly clean. It is quasi-periodic, meaning it wobbles and changes in intensity. Those subtle imperfections are the real treasure. They contain encoded information about the conditions in that final, violent plunge zone, details about magnetic field strength, plasma density, and temperatures that we could never measure directly. By deciphering the heartbeat's irregularities, we are essentially learning to take a black hole's vital signs. This rhythmic signal from a microquasar is more than a curiosity. It is a direct probe into the most chaotic environment possible, a place where the laws of physics are tested to their absolute limit. And its steady 50-second thrum is a reminder that even in the darkest acts of consumption, the universe can find a strange, compelling rhythm. The heartbeat is a steady drum, but some black holes speak in light we can barely see. After the historic first image of the supermassive black hole M87 star was revealed, a triumph of human collaboration, scientists expected the story to become clearer. Instead, a new layer of mystery emerged from the shadows, literally. Deep within the infrared portion of the spectrum, a strange and persistent glow surrounds the monster. This is not the brilliant light of its famous relativistic jet, nor the expected heat from its swirling accretion disk. This is something else, an unidentified infrared signature that clings to the black hole's immediate vicinity like a ghostly halo. Our best models of black hole physics, the very equations that predicted its shadow, struggle to account for it. The glow is too strong, too structured, or simply in the wrong place. It hints that our picture, while groundbreaking, is still missing crucial pieces of the puzzle. So what could be producing this enigmatic light? One possibility takes us into the realm of powerful magnetic fields. The environment just outside the event horizon of M87 star is a maelstrom of magnetized plasma. Theoretical work suggests that if these fields are even more tangled and energetic than we thought, they could accelerate electrons to near light speeds in complex ways, causing them to emit this excess infrared radiation. It would be like the black hole's magnetic personality shining through in a color we are only learning to see. Another, more speculative idea involves the very structure of the accretion flow. Perhaps the disk is not a smooth, continuous dinner plate of gas. It might be clumpy or have a hot, tenuous corona above and below it, similar to the atmosphere around our sun but infinitely more violent. This corona, heated by magnetic reconnection, could be bathing the region in this soft infrared glow. or could it be a signature of something falling in? As material finally crosses the event horizon, its last photon signals are stretched or red-shifted to longer, redder wavelengths by the black hole's immense gravity. Some of this stretched light could manifest as the faint infrared halo we detect, a final whisper from matter as it vanishes from our universe forever. This unidentified glow is more than a technical anomaly, it is a direct challenge. It tells us that near the point of no return, physics operates in ways we have not yet fully imagined. The first image was a silhouette, an outline of darkness. This infrared mystery is the first hint of the intricate, hidden details painted in that darkness, details we are only beginning to perceive. While infrared glows hint at hidden details, other black hole conversations are felt rather than seen. In May of 2019, the LIGO and Virgo gravitational wave observatories felt the universe itself shudder. The event was catalogued as GW 19021, a signal so massive it briefly saturated the detectors. This was the deep thump of two black holes colliding, one about 85 times the mass of our Sun, the other about 66 times. Their violent merger created a final black hole over 140 solar masses, sending ripples through the fabric of space-time that traveled for over 7 billion years to reach us. It was a monumental discovery, but it came with a profound silence. Across the globe, every telescope that could be pointed at the source region swiveled to look, hunting for a flash of light, a glimmer of X-rays, any electromagnetic whisper to accompany the gravitational roar. They found nothing. The merger was completely dark. This absence of light is what makes GW 19021 so puzzling and important. When two neutron stars merge, they produce a brilliant kilonova, a firework of heavy elements. When a black hole merges with a neutron star, it can tear its companion apart in a luminous display. But two black holes, in the purest sense, are just voids in space. Their collision should be a ghostly event, visible only through its gravitational footprint. So why did scientists expect to see something? The answer lies in the unusual masses of the parents. The 85 solar mass black hole sits squarely in what is called the pair instability mass gap. According to standard stellar evolution theory, stars that die with cores in this mass range should be completely obliterated by runaway nuclear reactions, leaving no remnant behind. That this black hole exists at all suggests it may have been born from a previous merger, a second-generation black hole. This possibility opened the door to a tantalizing scenario. If these black holes were born and lived within a dense stellar environment, like the core of a globular cluster or an active galactic nucleus, their merger could have been surrounded by gas. Imagine two dark sharks circling each other in a murky cosmic sea. As they spiraled together, their immense gravity would stir and heat the surrounding gas, potentially creating a brilliant flare of light just as they collided. The fact that we saw no such flare strongly suggests these black holes merged in a clean, empty void, a testament to their isolated and pristine nature. The silence spoke volumes. It told us that some of the universe's most violent events happen in perfect darkness, their only announcement a subtle tremor in the foundation of reality. GW 19021 was a conversation written entirely in gravity, a reminder that the deepest dialogues in the cosmos often leave no trace of light. The gravitational thump of a dark merger is one extreme, but a black hole's outburst can paint the entire sky. In June of 2015, a sleeping monster in our own galaxy woke with a vengeance. The black hole binary system V404 Cygni, about 7,800 light-years away, had been quiet for 26 years. Then it erupted into one of the brightest X-ray sources in the sky, a beacon of pure fury. Telescopes worldwide swiveled to watch, expecting a spectacular but predictable show of a black hole feeding. What they witnessed instead was chaos, a display so bizarre it seemed to defy physics. The X-ray light did not simply flare and fade, it flickered and pulsed with frantic, unpredictable intensity. But the real mystery was not just the flickering, it was what happened to that light afterward. Astronomers detected strange echoes like a scream bouncing through a labyrinth. The X-rays were being reflected, scattered, and delayed by unseen structures around the black hole, creating a complex hall of mirrors in deep space. These were not simple reflections off a static wall of gas. The echo patterns changed from hour to hour, sometimes from minute to minute. It was as if the clouds of gas swirling around the black hole were being violently reshaped in real time by the intense radiation blasting from the accretion disk. The leading explanation points to the black hole's corona, a mysterious region of superheated electrons just above and below the disk, thought to be the source of the high-energy X-rays. In most models, this corona is relatively stable, but at V404 Cygni, the outburst was so powerful it may have blown the corona apart. Imagine a volcano so violent it shatters its own crater. The intense radiation could have physically pushed clouds of gas outward, creating a turbulent, expanding fog that then reflected the subsequent flashes of X-rays. Each new flare would then illuminate a different part of this chaotic, moving scenery, producing the rapidly shifting echo pattern. Another possibility is that we are seeing the inner accretion disk itself warp and wobble under the intense pressures, casting moving shadows and creating complex reflection geometries. This event was a revelation. It showed us that the environment around a feeding black hole is not just hot and violent, it is dynamically unstable on human timescales. We were not looking at a static painting of a black hole's meal. We were watching a storm-tossed sea with waves of gas and radiation crashing against each other. The echoes from V404 Cygni are a recording of that storm, a distorted soundtrack that challenges us to rebuild our models of chaos from the reflections it leaves behind. The echoes from V404 Cygni showed us a storm in real time, but some signals carry the birth pangs of a new darkness. On February 18, 2006, satellites detected a gamma-ray burst, an event so common in the distant universe it was given a simple catalog number, GRB060218. At first, it seemed unremarkable, a long, faint flicker in the gamma-ray sky. But as astronomers raced to point other telescopes at its location, they realized this burst was an orphan, a cosmic oddball that did not fit into any known family. Typical gamma-ray bursts come in two violent flavors. Long bursts lasting more than 2 seconds are thought to be the death cries of massive stars as their cores collapse into black holes. Short bursts under 2 seconds are likely the mergers of neutron stars. GRB060218 was a long burst, but it was incredibly weak, hundreds of times fainter than its peers. And it was strangely close, originating in a galaxy only 440 million light-years away, practically in our cosmic backyard for such events. This proximity should have made it blindingly bright, yet it was a dim whisper. As optical telescopes caught up, they witnessed the expected sign of a dying star, a supernova, dubbed SN 2006-AJ. But the pieces did not add up. The gamma-ray signal and the supernova light were entangled in a way that defied the standard model. In the classic story, a massive star's core collapses, forms a black hole or a neutron star, and drives a jet of material out through the star at nearly the speed of light. This jet, piercing the star's outer layers, creates the initial gamma-ray burst. The star then explodes as a supernova hours or days later. For GRB060218, the timeline was all wrong. The weak gamma rays and the supernova light emerged together over a protracted period of days, as if the explosion was happening in slow motion. This bizarre signal profile points to a far more tortured birth. The leading theory is that we witnessed not a clean jet piercing a star, but the difficult, struggling formation of a newborn black hole itself. Imagine a star so massive that its core does not collapse instantly. Instead, it might have formed a temporary, unstable neutron star that wrestled against its own gravity for days, accreting more material from the falling star before finally succumbing and collapsing into a black hole. This prolonged death rattle would produce a weak, drawn-out stream of gamma rays as the central engine sputtered to life, all while the outer layers of the star were beginning their slower supernova expansion. It was a stellar death in two agonizing acts broadcast simultaneously. Another possibility is that the jet was choked, unable to punch cleanly out of the star. It might have been smothered by the stellar material, releasing its energy over a much longer time and heating the expanding debris from within, which would explain the coupled emission. GRB 060218 remains a critical outlier because it refuses to follow the script. Its faint, long signal is a detailed recording of a stellar core's final, failed struggle against oblivion, a rare glimpse of a black hole being born not with a brilliant shout but with a protracted, gasping whisper. The struggle of a black hole's birth is one thing, but the mature glow of an established monster holds its own secrets. From one of the most famous black holes in our galaxy, Cygnus X1, comes a signal that warms the quiet spaces of the microwave sky. This is not the high-energy X-ray radiation for which the system is known, but a persistent, anomalous microwave hum. It is a whisper of warmth in a band of light we associate with the faint afterglow of the Big Bang itself, coming from a region of violent death. So what is heating up the neighborhood around this black hole? The most straightforward answer points to the system's powerful relativistic jet. Cygnus X1 is a microquasar, a scaled-down version of the giant active galaxies, and it fires a narrow beam of charged particles at nearly the speed of light. As these electrons spiral around the jet's magnetic field lines, they emit synchrotron radiation, a broad spectrum of light that can easily extend into the microwave band. This would be the expected roar of the jet, simply heard in a different register, but the signal has peculiarities that suggest something more curious might be at play. Some astronomers have proposed a far more exotic source, spinning cosmic dust. Imagine the space around the black hole filled with tiny, icy or carbon-rich grains, the remnants of shattered asteroids or comets drawn into the system. Bathed in the intense radiation from the hot accretion disk and the jet, these microscopic particles would not just heat up, they would begin to spin at incredible rates, billions of rotations per second. This frantic spinning would cause them to emit microwave radiation in a very specific way, creating the anomalous hum we detect. It is a strange thought, the most destructive force in the local universe, powering a frenetic ballet of dust motes. The presence of this microwave emission does more than just puzzle us, it acts as a tracer. It maps out the cold, dusty material that coexists with the plasma inferno, revealing the full ecosystem of the black hole's domain. We see not just the blazing hot gas in the act of falling, but the colder, remnant debris that orbits at a safer distance, still dancing to the monster's tune. This signal forces us to see Cygnus X1 not as a simple point of X-ray light, but as a complex factory where extreme gravity, magnetic fury, and simple dust interact in a symphony across the entire electromagnetic spectrum. The microwave whisper is a reminder that even the darkest hearts can have a faint, warm glow. The warmth of spinning dust is a quiet mystery, but the sound of a star being torn apart is a deafening announcement. In November of 2014, a robotic telescope survey caught a sudden, brilliant flare in a distant galaxy nearly 300 million light-years away. This was Assassin 14 Li, a tidal disruption event, one of the most violent spectacles in the cosmos. A star had wandered too close to a supermassive black hole, and the black hole's immense tidal forces had stretched and shredded it into a long, spiraling streamer of gas. For months, astronomers watched the aftermath in visible light and X-rays, expecting the predictable glow of that debris raining down and heating up. But then, radio telescopes heard something extraordinary. Amid the chaotic roar of the destruction, they detected a signal of startling order, a series of periodic radio pulses repeating every 131 days. It was a metronome ticking inside a hurricane. This rhythm posed a profound question. When a black hole consumes a star in such a messy, asymmetric way, what could possibly create such a clean, repeating signal? The debate centers on two compelling possibilities, each pointing to a different fundamental property of the hidden black hole. The first theory involves the black hole's feast creating a powerful jet. As the stellar material falls in, some of it can be blasted away in two narrow, oppositely directed beams of plasma at nearly light speed. In the chaotic aftermath of a disruption, this jet might not be stable. If the black hole is spinning rapidly, it could drag the inner part of the accretion disk, causing the base of the jet to wobble or precess, like a spinning top slowly tracing a circle. As this precessing jet sweeps across our line of sight, its brightness would rise and fall with clockwork regularity, creating the 131-day radio pulse we observe. It would be a lighthouse beam from a dying star's funeral pyre swinging through the darkness. The second, even more intriguing idea points directly to the black hole's spin itself. The periodic signal could be a direct imprint of the monster's rotation. The theory suggests that the shredded star formed a temporary, lopsided accretion disk. As this disk orbits, its strongest emission might be beamed in a particular direction by relativistic effects. If the disk is misaligned with the black hole's spin axis, the dragging of space-time around the rotating black hole could cause the entire disk to wobble in a steady rhythm. Every 131 days, the brightest part of this wobbling structure would face Earth, giving us a periodic flash. In this scenario, the pulse is not from a jet, but from the very fabric of space-time, twisted by the black hole's rotation, orchestrating the glow of the debris. Distinguishing between these two ideas is crucial. A precessing jet tells us about the powerful outflows from such events, while a signal tied directly to spin gives us a rare, direct measurement of one of a black hole's only two fundamental properties, its mass and its spin. The periodic pulses from Assassin 14 Li transformed a catastrophic event from a simple flash into a complex, rhythmic signal, offering a potential key to unlock the secrets of a spinning singularity as it dines on a star. The rhythmic pulse of a black hole's feast is one thing, but a flash of dark lightning is a whole other kind of fury. From the hearts of the most active galaxies, where supermassive black holes fire jets of plasma across millions of light years, scientists are hunting for a phenomenon that sounds like science fiction: dark lightning. This is not lightning as we know it on Earth, born from water vapor and charged clouds. This is a far more violent process, a sudden, catastrophic release of gamma rays, the most energetic form of light, generated within the magnetic storms of a black hole's jet. The concept borrows its name from a terrestrial mystery: terrestrial gamma ray flashes, those brief, intense bursts of radiation that shoot upward from our own thunderstorms. In that familiar setting, powerful electric fields in storm clouds accelerate electrons to near light speed, and when these electrons collide with atoms, they can release a flash of gamma rays. Now scale that idea up to a cosmic nightmare. Within the magnetized chaos of a relativistic jet, conditions are perfect for an unimaginably more powerful version of this process. The jet is a natural particle accelerator, far more potent than anything we could build on Earth. As electrons and positrons are whipped through the jet's twisted magnetic fields, they can be accelerated so violently that they produce a brilliant, focused burst of gamma rays, a stroke of dark lightning within the beam. Detecting this specific signature is a monumental challenge, as it is buried within the already intense glow of the jet, but the payoff would be immense. These flashes could be the hidden engines that produce some of the universe's most mysterious travelers, ultra-high-energy cosmic rays. These are atomic nuclei, mostly protons, that streak across the universe with energies millions of times greater than anything produced in our largest particle colliders. For over a century, their origin has been one of astrophysics' greatest puzzles. Where in nature is there a particle accelerator this powerful? The dark lightning in black hole jets is a prime suspect. Each theoretical flash could act like a cosmic railgun, injecting protons and other nuclei with impossible energy, flinging them across intergalactic space. To find proof, astronomers are combing through data from gamma-ray telescopes like the Fermi Space Telescope, looking for telltale flickers within the steady roar of active galaxies. They search for a specific pattern, a sudden spike in the highest energy gamma rays that coincides with changes in the jet's radio or X-ray output, a sign of magnetic reconfiguration inside. It is a search for a ghostly spark within a torrent of fire, a single crack of thunder in a hurricane that has been blowing for 10 million years. If we can catch one of these flashes in the act, we will have found a direct link between the most destructive engines in the cosmos and the invisible, high-energy particles that constantly rain down on our planet, a fundamental connection written in bursts of light we are only learning to see. Dark lightning may crackle within jets, but one ghostly particle carried a message from a far more distant and violent source. On September 22, 2017, a single, nearly massless particle struck the ice deep beneath the South Pole. It was a neutrino, a ghost of the subatomic world, famous for passing through entire planets without a single interaction, but this one was different. It carried an immense energy, over 290 trillion electron volts, and it did not slip through unnoticed. It smashed into an atom in the pristine Antarctic ice, creating a faint, telltale flash of blue light captured by the Ice Cube Neutrino Observatory's thousands of sensitive detectors. This event, catalogued as Ice Cube 170922A, was extraordinary on its own, but the real story began when astronomers raced to trace its path back across the cosmos. The neutrino pointed like a cosmic arrow to a patch of sky in the constellation Orion. There, they found a blazing monster, a blazar known as TXS 0506+056. A blazar is the most extreme type of active galaxy where a supermassive black hole, billions of times the mass of our Sun, is firing a jet of plasma directly at Earth. We are staring straight down the barrel of a cosmic cannon. For decades, scientists had theorized that the chaotic environments around black holes, especially in their powerful jets, could be the accelerators for both high-energy cosmic rays and the neutrinos that should accompany them. This single event, Ice Cube 170922A, was the first solid proof. That one ghostly particle was a direct messenger from the heart of that jet, a tiny piece of shrapnel from a magnetic explosion occurring 4.5 billion light-years away. The mystery lies in the sheer improbability of the detection and what it tells us about the engine's fury. To produce a neutrino with that much energy, protons must be accelerated to near light speed within the jet and then collide with other particles or photons. That collision creates a cascade of secondary particles, including pions, which then decay into gamma rays and neutrinos. The neutrino we caught was one of countless trillions produced in that single event, the sole survivor of a 4.5 billion-year journey to reach our ice. Its detection confirmed that black hole jets are indeed cosmic particle accelerators of almost unimaginable power, but it also presented an unexplained channel of information. Why was this neutrino so bright? Why did it arrive when it did? Follow-up observations showed the blazar was in a heightened state of gamma-ray activity, but not the most extreme outburst ever seen. This suggests the process of neutrino production is not simply tied to the raw brightness we see in light. It hints at hidden, violent mechanisms within the jet, perhaps magnetic reconnection events or shock waves traveling down its length, that are uniquely efficient at forging these ghost particles. This single detection opened an entirely new window onto black holes. We are no longer just studying the light they emit or the gravitational waves they create. We are now catching the subatomic byproducts of their most violent internal processes. Each high-energy neutrino is a direct telegram from the particle acceleration zone itself, a place so turbulent and dense that not even light can give us a clear picture. IceCube 170922 was more than a lucky strike. It was a key, unlocking a new way to listen to the universe's most powerful engines, one ghostly whisper at a time. That single neutrino was a messenger from a modern cosmic engine, but some signals carry echoes from the very dawn of time. Deep in the quiet outback of Western Australia, a simple table-sized antenna named Edges listened to a frequency most radio telescopes ignore, the 21-centimeter line. This is the natural hum of neutral hydrogen, the most basic element in the cosmos. By tuning to this ancient channel, astronomers hope to hear the faint signature of the universe's first stars switching on over 13 billion years ago. What they heard instead was a whisper that shook the foundations of cosmology. The signal was there, a dip in the radio spectrum showing the first starlight heating the primordial hydrogen fog. But the dip was far too deep, more than twice as strong as any standard model of the early universe could possibly explain. It was as if the ancient cosmos was much, much colder than anyone predicted, or the first starlight was far more intense. This anomaly is not just a minor discrepancy, it is a gaping hole in our understanding of the universe's infancy. To explain such a profound chill in the early hydrogen, something must have been siphoning away its heat long before those first stars ignited. This is where the shadows of the earliest black holes enter the picture. One of the most compelling and wild theories involves primordial black holes. These are not the stellar mass black holes formed from dying stars, but hypothetical monsters born in the first chaotic second after the Big Bang itself, from the raw density fluctuations of the newborn cosmos. They could range in size from a small asteroid to many times the mass of our Sun. If a population of these ancient black holes existed, and if they were made of dark matter, they could have been the universe's first refrigerators. As they moved through the sea of hydrogen, their gravity would attract and compress the gas. But more importantly, if they were charged or possessed other exotic properties, they could have transferred energy away from the hydrogen, cooling it dramatically. Imagine these dark, primordial seeds scattered throughout the infant universe, acting like cosmic ice cubes, chilling the gas and making the eventual glow of the first stars appear, in our data, impossibly stark against a colder background. Another theory suggests radiation from the black holes themselves, perhaps from their accretion or from Hawking radiation if they were very small, could have altered the hydrogen's energy state to create the exaggerated signal. The Edges result remains fiercely controversial, with many scientists questioning the instrumentation or searching for more mundane terrestrial interference. But if it holds, and if primordial black holes are the key, then this faint radio whisper is the oldest signal we have ever detected. It is not a message from the first starlight, but a fingerprint of the darkness that preceded it, a direct echo from an era when the universe was not even a billion years old, and its true architects may have been trillions of silent, ancient black holes. A cosmic magnifying glass can sometimes reveal a hidden flaw in the lens itself. Gravitational lensing is one of Einstein's most spectacular predictions, where a massive object like a galaxy cluster bends the light from a more distant object behind it. The result is often beautiful, creating arcs and multiple images of a single galaxy, stretched and mirrored across the sky, but sometimes the math does not add up. Astronomers will map the visible mass in the foreground cluster, all the stars and glowing gas, and calculate how much distortion it should create. Yet in certain patches of sky, the observed warping is far too severe. The background light is bent more sharply than the visible mass can possibly explain. It is as if you placed a real magnifying glass on a page, and the words beneath it stretched even more than the glass's shape should allow, hinting at a hidden, denser layer embedded within the lens. This anomaly points to a massive presence that emits no light, a shadow within a shadow. The prime suspect is a rogue, intermediate mass black hole wandering through the cluster's heart. These are the elusive middle children of the black hole family, too large to be born from a single star, yet smaller than the supermassive giants at galactic centers. They could weigh anywhere from 100 to 100,000 times the mass of our Sun. One such object drifting unseen through the cluster would warp the space around it with tremendous gravity, amplifying the lensing effect in its immediate vicinity. Imagine a single, incredibly dense lead weight sewn into the fabric of a large lens, its concentrated mass creating a tiny, intense pinch in the image. That is what astronomers believe they are detecting, a localized knot in the gravitational field that betrays the black hole's path. These lensing anomalies are more than just evidence of a missing mass, they are a ghostly signature of a specific kind of monster. The black hole is not actively feeding, so it produces no X-rays or radio screams. It is not at the center of a galaxy, so it has no starry backdrop to betray its position. It is a dark wanderer, a solitary pit of gravity drifting silently through intergalactic space. Its only crime is bending the light that passes by, leaving a forensic fingerprint on the distorted images of galaxies billions of light years further away. Finding these anomalies is like noticing a single, sharper ripple on a pond's surface and deducing that a heavy, submerged stone must lie beneath. Each detection is a triumph of inference, proving that even in the act of revealing the distant universe, the cosmos can also reveal the dark travelers hiding in the foreground, their presence written only in the warped paths of ancient light. Our own galactic center holds an imprint of ancient violence on a scale we can barely comprehend. Stretching 25,000 light-years above and below the plane of the Milky Way, two colossal spheres of gamma-ray glow loom like silent ghosts. These are the Fermi bubbles discovered by the Fermi Gamma-Ray Space Telescope in 2010, and they are a monumental signal from our black hole's past. Each bubble is a titanic structure, large enough to contain entire dwarf galaxies, and they shine with the highest energy light in the universe. Their very existence is a billboard announcing that Sagittarius, a star, our quiet neighbor, was once a raging monster. The leading theory is clear: a past eruption. Sometime between a few million and a few 100,000 years ago, our supermassive black hole experienced a period of intense feeding, gorging on a massive cloud of gas or even a star cluster. This feast would have generated a pair of relativistic jets or a gargantuan wind of hot plasma, blasting outward from the galactic center at nearly the speed of light. These outflows punched through the thin gas of the Milky Way's halo, creating vast shock waves that, even today, accelerate particles to near light speed. When these ultra-fast particles collide with starlight or magnetic fields, they generate the gamma rays we now see as the bubbles, so the mystery is not really their origin, but their bizarre and uneven personality. If this was a single, symmetrical explosion from a central engine, we would expect the bubbles to be smooth, uniform shells. They are anything but. The gamma-ray glow is patchy, with sharp edges in some places and fuzzy boundaries in others. The bubbles are not perfectly aligned with the galactic center, and their internal structure is laced with filaments and knots of brighter emission. This complex texture is the real puzzle. It suggests the eruption was not a clean, steady blast. It might have been a series of violent hiccups, with the black hole firing off multiple jets in slightly different directions over thousands of years, creating overlapping layers of shocked gas. Or the environment through which the bubbles expanded was not a clean, empty void. The Milky Way's halo is filled with a thin, magnetized gas and dark matter. As the bubbles inflated, they would have encountered pockets of denser material, like a balloon expanding through a cloud of cobwebs. These interactions could have sculpted the bubble's edges, creating the lumpy, uneven structure we observe. Some of the brightest filaments might even be the scars of ancient magnetic field lines, glowing where they were compressed and energized by the passing shockwave. The signal from the Fermi bubbles is therefore a palimpsest, a single image written over multiple events. We are seeing the combined aftermath of a black hole's tantrum and the texture of the galactic medium it erupted into. This changes our understanding of our home galaxy's history. The Milky Way is not a serene spiral. It is a system still bearing the scars of a central cataclysm that occurred long before humans walked the Earth. Those faint gamma-ray ghosts are a permanent reminder that even the quietest cosmic giants have a violent youth written across the sky. The Fermi bubbles are a monument to past violence, but some black holes announce their inner turmoil with a sudden, profound silence. In the constellation Ophiuchus, a stellar mass black hole named Maxi J1820+070 was putting on a spectacular show. It had been devouring material from its companion star for months, glowing brilliantly as one of the brightest X-ray sources in the sky. Astronomers were watching closely, tracking the predictable rhythms of its feast. Then, in late 2018, it did something utterly unexpected. It simply turned off. The brilliant X-ray corona, that halo of superheated electrons above the disk, vanished in a matter of days. The black hole did not fade gradually as its meal ended. It was as if someone flipped a switch, plunging the inner engine into darkness while material was still clearly flowing in from the companion star. This event is called X-ray quenching, and it was a direct challenge to every standard model of black hole accretion. We thought we understood the dinner bell. As gas spirals inward, it heats up, eventually forming a searing corona that emits high-energy X-rays. The brighter the inflow, the brighter the corona should glow. Maxi J1820 broke that rule completely. Observations showed that the accretion disk itself, the swirling flow of gas, was still present and shining in optical and ultraviolet light. The meal was still being served, but the black hole's most energetic table manners had abruptly stopped. So what caused this sudden electrical fault in the cosmic power plant? The leading theory points to a radical change in the inner disk's very structure. Imagine the accretion disk as a river flowing toward a waterfall. Closer to the black hole, the flow becomes turbulent and hot, creating the corona. The new idea suggests the inner part of that river might have suddenly changed state. It could have transitioned from a hot, puffy, magnetically dominated plasma into a cool, dense, and geometrically thin flow. In this cool state, the energy from friction gets converted into optical light rather than being used to heat the corona. It is like a boiling pot of water suddenly settling into a calm, simmering state, no longer producing a cloud of steam. The switch could be triggered by a slight change in the accretion rate, a magnetic reconfiguration, or some other instability we do not yet fully understand. Another possibility is that the corona itself did not vanish but was somehow obscured. Perhaps a dense, cold wind of material blew outward from the inner disk, forming a shroud that absorbed the high-energy X-rays before they could escape, while allowing lower-energy light to pass through. We were left seeing the glow of the dinner plate, but not the scorching heat of the oven. This sudden quenching is more than a glitch, it is a revelation. It tells us that the environment around a black hole can exist in distinct states and can flip between them rapidly and dramatically. The black hole's appetite remained, but its method of consumption transformed before our eyes. That quieting of the X-rays was not an end, but a transition into a different kind of darkness, one that forced us to rewrite the manual on how these gravitational engines truly operate. Across the vast canvas of the sky, a strange and beautiful pattern emerges, one that seems almost too perfect to be random. Astronomers mapping powerful radio galaxies have noticed something peculiar. A handful of these brilliant sources appear to line up with uncanny precision, like luminous pearls on an invisible cosmic string. This alignment, known informally as the string of pearls, is a statistical headache, a configuration so orderly it challenges our understanding of how the universe distributes its most violent objects. The probability of such a perfect line occurring by pure chance is vanishingly small, which means something must be orchestrating this celestial geometry. The most conventional explanation points to a filament of the cosmic web, the vast network of dark matter and gas that forms the large-scale structure of the universe. Galaxies and the supermassive black holes at their hearts are known to form along these filaments. Perhaps we are simply looking down the length of one particularly dense and active strand, seeing the black holes within its galaxies all flaring in radio waves at once, creating the illusion of a deliberate string. But the alignment is so sharp and the sources so evenly spaced that some theorists have dared to propose far more exotic origins. One radical idea reaches back to the universe's first moments, to cosmic strings. These are not strings of matter, but hypothetical, one-dimensional defects in the fabric of space-time itself, relics from the phase transitions of the early cosmos. Predicted by some theories, a cosmic string would be a flaw in reality, thinner than an atom but stretching across the entire universe with immense gravitational density. If such a string exists and passed through a galaxy cluster, its immense gravity could trigger star formation and ignite black hole activity along its length, lighting up a series of radio galaxies at precise intervals. It would be a scar on space-time, revealed by the beacons of black holes it awakened. An equally mind-bending alternative suggests the pearls are not galaxies at all, but the graves of the universe's first monsters. The string could be a chain of primordial black holes, those ancient relics born from the Big Bang's raw density. If a line of these dark fossils survived from the infancy of everything, their collective gravity could attract and compress gas over eons, eventually sparking the radio-loud outbursts we see. We would be witnessing not a structure that formed black holes, but a structure made of black holes, a necklace of singularities woven into the cosmos at its creation. The controversy is intense because the stakes are foundational. If the string of pearls is evidence of a cosmic string, it would be a direct detection of a feature from a time a fraction of a second after the Big Bang, confirming theories of how the fundamental forces separated. If it is a chain of primordial black holes, it could solve the dark matter mystery, revealing that the unseen mass of the universe is tied up in these ancient knots of gravity. Yet skepticism remains high, for the human mind is exceptional at finding patterns, even where none exist. The alignment could still be a cruel trick of perspective, a chance configuration we have imbued with meaning because its elegance is so compelling. For now, this celestial necklace hangs in the data, a beautiful enigma. It asks us whether the universe's largest structures are merely random scatter, or if, on the grandest scales, there is a hidden geometry, a ghostly architecture written in the fire of black holes. Even the most reliable cosmic clocks can sometimes skip a beat. Pulsars, the rapidly spinning corpses of massive stars, are the universe's ultimate timekeepers. Their rotations are so stable that the tiny pulses of radiation they emit can be predicted with precision down to the microsecond, rivaling the best atomic clocks on Earth. But this reliability is what makes a single misfit so profoundly interesting. Pulsar J1640-4631, a young, powerful pulsar in the constellation Norma, is sending a signal that defies the most fundamental models of how these objects should age. Every pulsar slows down over time, a gradual spin down caused as its powerful magnetic field acts like a brake, radiating energy away into space. The rate of this slowdown is described by a number called the braking index. For a simple, isolated pulsar spinning in a perfect vacuum, this index should be exactly 3. It is a cornerstone of pulsar physics, but for J1640, the braking index is not 3. Measurements show it to be significantly lower, around 2.1. This is not a small measurement error, it is a glaring anomaly, a direct signal that something is wrong with our basic picture. The pulsar is slowing down faster than the standard model allows, so where is that extra energy going? If the magnetic brake alone cannot account for it, something else must be stealing rotational energy from the pulsar. This is where the shadow of a dark companion emerges. The most compelling explanation is that pulsar J1640 is not alone. It may be locked in a tight, invisible dance with a black hole. In this scenario, the two objects orbit each other rapidly, and as they do, they ripple the fabric of space-time itself, generating a constant stream of gravitational waves. Producing these waves requires energy, and that energy is being drained directly from the pulsar's spin, causing it to slow down faster than expected. It is as if you were pedaling a bicycle, but someone has secretly attached a powerful generator to the wheels, siphoning off your effort into an invisible current. The anomalous braking index becomes a fingerprint of that theft. Every extra bit of slowdown we measure is energy being converted into the silent hum of gravitational radiation. But the plot thickens because the signal is not just about energy loss. The presence of a massive, close companion like a black hole would also warp the space around the pulsar, subtly altering the path its radio pulses take to reach us. This could create additional, more complex distortions in the timing of the pulses, beyond the simple orbital wobble we would expect. Scientists are now searching for these subtle effects in the data, looking for the unique signature of space-time curvature caused by a nearby singularity. Finding it would be a monumental discovery, a direct detection of a black hole through its gravitational influence on a lighthouse of light. Pulsar J1640's strange spin down is more than a broken clock. It is a potential window into a hidden binary system, where a beacon of radiation is being slowly wound down by the silent, relentless gravity of its dark partner. The perfect silence of a black hole merger is a profound statement, but astronomers are listening for a whisper that might break it. They are hunting for the theoretical afterglow of a binary black hole collision, a faint flash of light that would finally illuminate the dark process of two singularities becoming one. The gravitational wave signal tells us the when and the where of the merger, but an electromagnetic counterpart would reveal the how and the what of the environment, turning a tremor into a full-color picture. The concept is straightforward in theory. Imagine two black holes orbiting not in a perfect vacuum, but within a common cloud of gas, perhaps the remnant of the stellar nursery that birthed them, or material captured later in their cosmic lives. As they spiral together in their final moments, their immense gravity violently stirs this surrounding gas, heating it to extreme temperatures. When they finally merge, the newborn, more massive black hole receives a powerful kick, like a rocket recoiling from a blast. This recoil can send it plowing through the hot gas at tremendous speed, creating a shock wave. That shock wave, in turn, could produce a brief flare of light across the spectrum, from radio waves to X-rays. This would be the smoking gun, a direct electromagnetic signature of the merger itself. Yet, despite dozens of gravitational wave detections from black hole mergers, this predicted afterglow has never been conclusively seen. Its elusiveness is itself a critical clue. It tells us that the vast majority of stellar mass black hole binaries merge in exceptionally clean environments, devoid of significant gas. They are like two sharks circling in the open ocean, leaving no trace of their final collision. This makes sense for black holes born from massive stars in isolated systems, where any leftover gas would have been blown away by stellar winds long ago. The search, however, continues because finding just one example would revolutionize our understanding. It would confirm that some black hole pairs do form and evolve in gas-rich settings, like the dense disks around active galactic nuclei. It would allow us to measure the kick velocity of the newborn black hole directly, revealing the asymmetry of the merger. Most importantly, it would give us a precise location on the sky, enabling telescopes to study the host galaxy and the aftermath in exquisite detail. The hunt focuses on following up gravitational wave alerts with incredible speed, scanning the vast error box in the sky for any unusual flicker of light. It is a search for a needle in a cosmic haystack where the needle might only glow for a few hours. This missing afterglow is a ghost we chase, a signal that remains trapped between our theoretical predictions and the universe's quiet preference for darkness. Its continued absence speaks to the lonely deaths of most black holes, but the hope of finding it keeps our telescopes pointed at the void, waiting for a single, brilliant exception to prove the rule. The universe's rhythm section just gained a new, deeply strange instrument. Astronomers have begun to catch signals that operate on a timescale we can finally feel in our bones, signals that pulse not in milliseconds or years, but in the slow, patient cadence of a full Earth day. These are the ultra-long-period radio transients, mysterious sources that flicker on over the course of hours, shine for a day or more, and then fade back into silence for weeks or months. They are not the rapid fire ticks of pulsars or the brief screams of FRBs. They are the slow, deep breaths of something colossal and hidden. The mystery is absolute because when telescopes swing to look at these spots in every other wavelength of light, they find nothing. No star, no nebula, no X-ray glow, just an empty patch of sky that, for a brief window, sings a powerful radio song. What kind of cosmic engine operates on such a leisurely yet powerful schedule? The leading theories point directly to the complex dances of black hole binaries, but with a twist so extreme it redefines patience. Imagine a system where a black hole and a companion, perhaps a neutron star or another black hole, are locked in an orbit of staggering size. Their orbital period could be months or even years. Now, picture that the black hole is actively feeding, pulling a stream of gas from its partner into an accretion disk and launching a jet. If that jet is unstable or if the feeding process is intermittent, the system might only become visible in radio waves when the stars align, quite literally. During a specific phase of their long orbit, when the companion is closest, the stream of stolen material might surge, igniting the jet like a pilot light flaring to life. For the days or weeks of this close encounter, the radio beacon shines only to dim as the stars swing apart again on their epic celestial waltz. An even more exotic possibility involves not the orbit, but the jet's own slow-motion wobble. A rapidly spinning black hole can drag space-time around it, causing the entire accretion disk and the jet launching from it to precess, like a spinning top slowly tracing a circle. If that precession period is very long, say several weeks, then the powerful beam of the jet might only sweep across our line of sight for a brief window during each cycle. For that time, the source is brilliantly bright to our radio telescopes. Then, as the beam continues its slow sweep across the cosmos, it points away from us and the signal vanishes for another cycle. We would be witnessing a cosmic lighthouse with a rotating lens so vast its beam takes months to complete a single sweep. The sheer scale implied is breathtaking, suggesting the involvement of a supermassive black hole in a delicate, slow-motion ballet. These ultra-long-period transients are more than just a new class of object. They are a challenge to our observational patience. Our telescopes are built to catch rapid bursts or monitor steady sources, not to track signals that emerge and vanish on a human schedule. Discovering them required new ways of sifting through data, looking for patterns that unfold not in seconds but in seasons. Each one we find is a clue that the most dramatic cosmic events are not always the fastest. Some of the universe's most powerful engines operate with a slow, deliberate rhythm, turning on for a day as if marking time in a calendar we are only just beginning to read. Their patient glow suggests entire classes of hidden binary systems, moving in stately, silent orbits until the moment their gravity pulls the trigger on a signal that lasts just long enough for us to notice. The cosmic microwave background is the oldest photograph of our universe, a snapshot from its infancy. Yet within this serene glow of ancient light, astronomers have found a blemish, a place where the temperature drops in a way that simple physics cannot explain. This is the cold spot, a vast region of space hundreds of millions of light years across that is significantly colder than the surrounding cosmic backdrop. Its existence is a statistical anomaly so profound it suggests something massive, something strange, intervened in the early cosmos. The most conventional explanation is a cosmic void, an immense bubble of relative emptiness where fewer galaxies and less matter pull the fabric of space. As light from the cosmic microwave background travels through such a void, it loses energy climbing out of the gravitational well, a process that would make the region appear colder to us. Yet surveys have struggled to find a void large enough and empty enough to account for the cold spot's extreme chill. Its scale defies what we understand about the growth of cosmic structure. This failure of the simple void model has opened the door to ideas that sound like science fiction. One of the most radical theories proposes that the cold spot is not a feature of our universe at all, but a bruise. It could be the imprint of a collision with another universe in the vast multiverse, a place where our cosmos was literally bumped by a neighboring reality during its inflationary expansion. The energy of that collision would have left a unique signature, a circular patch of cooler temperature in the cosmic background. While compelling, this idea is nearly impossible to test directly. But there is another, equally profound possibility that brings us back to the architects of darkness. Could the cold spot be the shadow of a primordial black hole of unimaginable scale? Not a stellar remnant, but a monster born in the first instance of time, so vast it could be considered a small universe in its own right. If such an object existed in the path of the ancient light, its immense gravity would have warped space-time, acting as a cosmic lens. It could have focused and redirected the paths of photons from the hot Big Bang plasma around it, creating a region that appears emptier and colder from our vantage point. Alternatively, the black hole's presence in the early universe might have suppressed the formation of galaxies in its vicinity, creating the supervoid we seem to detect, but for a reason far more exotic than mere chance. The black hole would not be the void itself, but the seed around which the void grew. Its gravity could have repelled normal matter in the primordial soup, clearing out a colossal region of space that later remained eerily empty. The cold spot, then, would be a fossil imprint of that ancient repellent force, a ghostly footprint left by a wandering titan from the dawn of everything. This idea connects the largest-scale mystery in cosmology to the most extreme objects in physics. It suggests that the answers to why our universe looks the way it does may be written not just in the diffuse glow of creation, but in the concentrated scars left by its first and most powerful singularities. The chill we detect is not merely an absence of heat, but perhaps the lingering shadow of a primordial giant that has been hiding in plain sight for over 13 billion years. Our universe's smallest, densest stars can sometimes cast the largest, most energetic shadows. Around a handful of aging pulsars, astronomers have mapped something that should not exist: vast, faint halos of tera-electronvolt gamma rays. These are photons with energies trillions of times greater than visible light, forming immense spherical clouds that stretch for dozens of light years. The pulsars themselves are known particle accelerators, their furious winds of charged particles creating a bubble of emission called a pulsar wind nebula. But these newly discovered halos are different. They are far larger, more symmetrical, and glow in an energy range that the pulsar alone seems too feeble to produce. It is as if a lone candle were found to be casting the shadow of a bonfire. The mystery lies in the sheer scale of the acceleration required. To generate gamma rays this powerful, particles, likely electrons, must be revved up to velocities achingly close to the speed of light. A solitary, spinning neutron star, no matter how magnetic, struggles to explain how this happens so efficiently across such a vast volume of space. Its energy appears to be spreading and amplifying in a way that defies our models. This is where a dark partner enters the stage. The leading hypothesis to explain these immense halos proposes that these pulsars are not alone. each could be locked in a binary dance with a black hole. In this scenario, the pulsar's relentless wind of particles does not simply blow out into empty space. Instead, it slams into the black hole's own influence, a surrounding medium of gas or a powerful magnetic field stirred by the unseen companion. This collision creates a colossal, standing shock wave that wraps around the entire system. Think of it like a boat speeding across a lake, its bow creating a V-shaped wake. Now imagine that boat is circling a massive, submerged turbine. The wake from the boat and the turbulence from the turbine would collide and mix, creating a chaotic, energetic region far larger than either object alone. That chaotic region is the particle accelerator. Within that merged shock front, particles from the pulsar wind get trapped and ricocheted back and forth, gaining a tremendous extra kick from the black hole's environment. Each pass through the shock injects more energy, eventually allowing them to emit the incredibly high energy gamma rays we see as the halo. The black hole itself remains dark and quiet, not actively feeding, but its gravitational presence and any material around it provide the essential wall for the pulsar's energy to crash against. Without it, the pulsar's wind would simply dissipate into the void, unable to create such a brilliant and structured glow. This explanation turns the halo from an anomaly into a partnership, a collaborative signal between a beacon of light and a well of darkness. Finding more of these halos and studying their shapes could reveal a hidden population of black hole binaries, systems where the most visible and the most invisible objects in the universe work in tandem to paint the sky with radiation of impossible strength. Each faint giant halo is a testament to a hidden dance, a signature written in the highest energy light that we are only beginning to decode. Closest to the monster's mouth, the strangest structure of all drifts like smoke. Near Sagittarius, a star within the chaotic heart of our galaxy, astronomers have mapped a bizarre thread of radio light. They call it the dragon's tail, a long, twisted filament that stretches for dozens of light years, coiling through the violent neighborhood of our supermassive black hole. It does not glow in X-rays from scorching heat, nor does it shine with the broad light of stars. It emits only a specific, polarized radio whisper, a sign that its light is born from electrons spiraling in a powerful magnetic field. This delicate, persistent thread hangs in the most turbulent place imaginable, and its very existence challenges our understanding of what can survive there. So what is this cosmic filament? Is it a scar on space-time, a relic of magnetic fury, or the ghost of a past cataclysm? One of the most exotic possibilities is that we are looking at a cosmic string, a hypothetical flaw in the fabric of the universe. If such a one-dimensional defect passed near our galactic center, its immense gravitational density could have attracted and heated gas, lighting it up along its length. The dragon's tail would then be a fossil from the universe's first moments, a crack in reality itself, draped casually near a black hole. While thrilling, this idea is a last resort for most scientists, as cosmic strings remain entirely theoretical. A more grounded, yet still profound, explanation paints the filament as a colossal magnetic flux tube. Imagine the space around Sagittarius, a star, as filled with a dynamic, invisible web of magnetic field lines, like the iron filings around a bar magnet, but on a galactic scale. Under the right conditions, these lines can bundle together, pinching off into a self-contained rope of magnetic energy. Electrons, accelerated by the black hole's activity, could then travel along this rope, spiraling around the magnetic field and emitting the synchrotron radio glow we see. The dragon's tail would be a cosmic electrical wire, a conduit for energy flowing through the galactic center, its twisted shape revealing the turbulent winds and pressures that sculpt it. But perhaps the most compelling story connects the filament directly to the black hole's own history. It could be the fading remnant of a past jet from Sagittarius, a star. Millions of years ago, during an eruption like the one that created the Fermi bubbles, our black hole may have fired a brief, misaligned jet. That jet of plasma would have punched into the surrounding gas, leaving behind a tunnel of magnetized, energized material. Over eons, the jet itself shut off, but this magnetic tunnel, this fossilized beam, remained. The dragon's tail would then be the ghost of that ancient outburst, a still glowing scar in the galactic flesh, showing us the direction of a blast that occurred long before humanity existed. Its delicate persistence is the real wonder. The environment around Sagittarius, a star, is one of immense forces, with stellar winds and gravitational tides that should shred such a structure in short order. That it endures suggests it is either incredibly resilient, held together by a powerful internal magnetic tension, or it is being continuously replenished by energy from the black hole's ongoing, subtle activity. Each observation of its subtle bends and kinks is like reading a history of the storms it has weathered. This radio filament is more than a curiosity, it is a probe. By studying its exact properties, its magnetic field strength, and how it interacts with the surrounding gas, we can indirectly measure the hidden forces at play in the black hole's backyard. It is a piece of string left in a hurricane, and by seeing how it flutters, we can deduce the wind patterns we cannot see. The dragon's tail is a silent witness, a fragile-looking thread that has somehow survived the dragon's breath, and in its quiet radio song, it holds clues to the tempestuous past and present of the dark heart of our Milky Way. These 25 signals are not just random noise from the cosmos. They are a catalogue of our ignorance, a map of the frontiers where our understanding of black holes dissolves into mystery. From the singular, brilliant wow signal to the patient rhythm of a black hole's heartbeat, each one forces us to rewrite a chapter in the book of astrophysics. We have heard the screams of shredded stars, the ghostly whispers of primordial chills, and the profound silence of dark mergers. We have traced a single particle back to a jet 4.5 billion light-years away and found potential architecture in the heavens written by black holes themselves. These are not puzzles to be solved and filed away, they are conversations. The universe is speaking in a language of gravity, light, and shadow, and we are only just learning to listen. Every unexplained flicker, every anomalous rhythm, every silent patch of sky is an invitation to look deeper, to think differently, to embrace the beautiful unknown that lies at the heart of our reality. Space will always hold more questions than answers, and that is its greatest gift, an endless frontier of wonder that stretches from the cold echoes of the Big Bang to the warm, spinning dust around a nearby monster. So tell us, which of these 25 cosmic mysteries pulled you in the most? Was it the patient dragon's tail at our galaxy's core, or the shocking heartbeat of a feeding singularity? Share your thoughts below, and if you are hungry for more journeys to the edge of understanding, be sure to subscribe. Our universe is full of stories, and the next signal is already on its way.